All right. So hello everyone. Welcome back to the section 5. So in this section, this is going to be our first section focusing on the theory part. And in this particular section, what we hope to do is to focus on the central difference method and also the derivation of the bar element. And central difference is a mathematical method that allows you to find, approximate the slope of a function at a given point. And then the bar element is probably one of that most widely used element, and we're going to learn how can we use the central difference to derive that bar element, given that we can find a formulation for the potential of the bar. So for the first part, we're going to start discussing and reviewing some of the knowledge about the potential of a deformable bar or a deformable spring. So probably back in, I don't know, high school physics or college physics, we've learned Hooke law, right? So basically for a spring, its reaction forces follows this equation. It's linearly correlated to the deformation, and the factor is a stiffness factor K. So if you have a spring, it's deformed by delta. The forces coming out of this would be K times delta. And also probably while we're a high school student, we already know that when the spring is compressed, it stores some potential energy or some strain energy inside that's capable of doing work or push some objects away, let's say. And that particular energy is described using this equation, 1/2 K times delta square. So the stiffness factor times the square of the deformation. And this energy is done by integrating the force times a lot of this little deformation step throughout the entire process. So we learned how to do this using the calculus or using integration basically a long time ago by this point, I believe, for most of you. And with that knowledge in mind, with the potential in mind, we've also remembered that if we take the first derivatives of these potential energy, we end up getting the forces. So basically that is take the derivatives about delta, and the function will be 1/2 K delta square, and there's going to be a 2. 1/2 K is the constant that never get changes, and the second order becomes the first order, right? So K delta, that's the result that we're getting. And then if we keep taking the netter derivatives, the second derivatives, it's going to become K delta, and that will give us a K at the end of the day. So the first derivative is the forces, whereas the second derivative is the stiffness. And that's true for one dimension when we use the one dimension representation, delta. That's also true if we extend everything to multi-dimension. So for instance, if we have a bar element, and the most logical way of representing this bar element is to represent it using the two nodal coordinates, right? So we might have an xi. So I will use the underscore to represent that this is a vector. So for the xi is basically xi, yi, zi. So these are scalar. The boat is the vector, and of course, the hand reason I'm not going to be able to write the boat form. So this would be the bar, right? Xi node and xj. That's the two nodal coordinates, and it probably deforms from another place, which is original place that has a stress-free length L naught there. So it's been deformed to these new location here. And then the new length with xi and xj, we can calculate it as using this equation on the left, right? So basically xi minus xj, square it, and then take the square root out of it. That would be the result of the new length of this particular bar. Or another way, if we're doing coding, we can say norm, and this would be a standard two norm of the system. Xi minus xj, two norm, and in coding, most likely in most of the code languages, if you use these, it will gives you that it would be using that equation to do the calculation. If you want to expand everything out, it would be this equation here. So this time it's going to be a scalar rather than a vector. So hopefully by now this is not too surprising and you're familiar with these. Then in order to cook up a energy, a potential for this bar element, what we do is we just replace this delta in this equation with these, right? That's shown here. And this actually could be done with just, I don't know, one line of code, and we can make it a function. So this is a potential calculation function. P is the output potential. We input xi, xj, those are 3x1 vectors. So that's this vector here. And the L naught is the original length of the bar, and K bar is the stiffness of that bar. So 0.5 times K bar times this thing here, which is the elongation or the shortening square norm of xi minus xj would be, in the code, how we create this equation here. All right, so far so good, right? Everything quite straightforward, right? So like we mentioned, once we have this potential here, the force factor is, just the first derivatives, right? But right now, if you take a look at this equation here, what you realize that we're actually dealing with 6 dimensions. So it's this potential is about xi, yi, zi, xj, yj, zj. So this is 6 dimension. So if we take the first derivatives, technically we're going to get the Jacobian of that term. And that result will actually directly give us the reacting forces on the node in each of the coordinate directions. So basically the F bar is the nabla x about nabla U bar about x, basically. So this inverse triangle is called nabla. I believe from multivariable calculus, you've been using these for quite a while. So okay, so this is going to give us that internal force, reaction force from the two nodes. So let me actually mark what we are looking at here. So this is basically the bar, right? So let's say if you have the nodal coordinate, this is your x, y, z dimension, then for xi node, you will have a force component that's in the x direction. You will have a force component in the y direction, and you will have a force in the zi direction. And the same thing with the xj node, so fzj, and then this is xj, and this is fyj. So that's j node, this is I node here. And hopefully, if you do the vector sum of these two components, you would end up having a force that's along, this is fj, a vector that has a direction that's along that bar. That's basically what you need to have if you do this right? Because remember, a bar or a spring, it only provides reaction forces along its own axial direction. And also the other thing you want to get is that the at the value of xi, the magnitude of xi is equal to the value from xj, right? Hopefully you get these two properties so that you know you have the right answer. But anyway, so this is how we get the xi, the forces in the xi, yi, zi, xj, yj, zj direction. We take the derivatives. So, but this time, what we need to do is to take derivatives about all these axes. So there's going to be 6 derivatives. And it's the derivatives of these equation here. That's the potential. It looks a little bit annoying. I don't want to do it, right? I've done it, I promise you. And if you go to the vectorized nodal elements that's provided in the package, it's there. But right now, I just want to save my time and I don't want to do it analytically. Are there things that I can do to solve it? So there is. And the method I'm going to introduce to you is called central difference. So that's one of the very handful and handy tool we can use to solve for these derivatives using numerical method. So central difference is a numerical method. So the underlying idea behind the central difference is basically just finding the slope or approximating the slope of a function. So let's say if we have a function like that, and let me draw another line. That's good. And for a given node, x hat, so this is x, that's the function about x. For a given node, I typically have a tangent, and that's the slope at these x hat position, right? And the way we find the slope here is usually find the derivatives and then of that f function and then put x hat into it and so forth. So this is how we would do analytically. So basically we find the derivatives of this equation and then we put the current node into this equation and try to see what value we get, right? So that's to solve this thing analytically. We don't want to do that. So what can we do without doing these? Central difference is a method to do that. And the way it works is you move a little bit, you move a step, delta forward from x hat, you move another step, delta backward from x hat, you calculate the function of the value of that function. So basically, there's going to be x hat plus delta, and then minus f x hat minus delta, right? So you evaluate the value of this function twice. One is a forward step, that's plus delta, and the other one is the backward step minus delta. So that gives you basically the f value for these two nodes, right? So this is f x hat minus delta. That's exactly the y-axis or for this node, and this thing will give you f x hat plus delta. And the slope, this two node point will gives you a second slope or and that will gives you a good way to approximate that f prime x hat as long as the delta is small. And to complete the calculation, we need to divide everything by 2 delta, which is the width at these x direction. So this is 2 delta. So that's the slope, right? This is a numerical way to approximate f prime x. So that's what we can use. And this method is called central difference. So if you're dealing with multi-dimensional system, it's still the same thing, and it's explained in these in this figure here. So for instance, if I want to find this value here, so basically the forces along the xi about the xi variable, what I'm going to be doing is I move xi plus forward by delta, this very small delta step, and I'm going to move xi backward by delta. I find the bar's potential using this u bar function. So basically, this function I created at the very beginning, u bar PE function. And after that, I subtract the from the forward step to backward step and divide the entire thing by 2 delta. So these give us the central difference approximation for the forces along the xi direction. So on and so forth for the yi direction. And when evaluating the potential function, I move yi forward by delta step, move yi backward by a delta step, and then minus it divided by 2 delta, and so on and so forth. So I repeat this thing for 6 times for both xi, yi, zi, and xj, yj, zj. And this function is created to achieve these. So let's see what we're doing. We have xi, xj, the nodal coordinates, the original length, the stiffness of the bar, and delta is this delta here. So we first create the x forward, which is the forward step. It's the xi plus delta. X backward is, again, xi minus delta. So we evaluate the potential function's value using x forward and xj. So that's basically using this function here. And we do that again for the backward step. Divide the difference between this potential by 2 and then by delta, and that gives us Fi. So for the node xi. So this part of the code is for node xi. This part of the code is for node xj. So we're doing these over 1, 2, 3. So that's for xyz direction. And when x is I, we kept compute the upper part computes these force here. So this part computes this force. And when x is 1, this second part will compute this force here. When x is 2, it's going to be these yi and yj. All right, so that's how we can understand it. So just keep in mind that for these functions, the xi and xj in the functions are a vector, so they are the bold letters, not the scalar xi, xj. So that's just one of the things I hope to clarify. So okay, so hopefully this looks straightforward to you, and we keep moving forward and see how these things works, right? And in the next 5.3 section, what I hope to do is to use an example to demonstrate how these function we just created works and evaluate whether or not that makes the result make sense or not. Okay, so let's assume that we have a bar. The original position of the bar, xi node is 0, 0, 0, xj node is 1, 0, 0, 0. So it's going to be lying along the x-axis with original length of 1. So in mechanics, typically for undeformed configuration, we also use the uppercase x to represent the undeformed configuration, and we use lowercase x to represent the deformed configuration. So this is the undeformed configuration, original length, k bar, and the delta. So one of the things I hope to point out here is that delta is very small. It's 10 to the negative minus 6 power, to the power of negative minus 6. So it's much, much smaller than the length of the bar, and that's typically what you need in order for the slope to give you to allow the central difference to give you an accurate enough approximation of the actual slope there. So here I'm defining the new nodal coordinate of the bar, xi, the deformed xi is still 0, 0, 0, so it's not moving. But the J node will move, and you have some flexibility in controlling where you want it to move. And the rest of the code is just to plot this original bar and the new bar location, and also to plot the forces using the Quiver3 function from MATLAB. So if you are unsure about how to use them, you can check out the MATLAB's website. It's going to give you how to use all of these functions. So eventually we end up at this result figure. So let's hide the code for now and try to play with it. So again, we can, rotate, change our view of angle, and then we can move the bar here and there. And let me actually make these to be 0, 0, and let's make this to be 1 for now. So what we're doing is we are deforming these second bar here into the 0, 0, 1 configuration. and of the J's node. So at this point, the bar still have a length of 1. Because the length is not changing, there's no forces coming out of the bar, right? You need to deform the bar to get forces. And if we extend it, you can see there's going to be tension forces. So these red arrows, they're indicating the force found by basically this function we previously created here. So using the local bar force function. So that's basically the bar force vector being plotted. And then if we, if we get that into smaller than 1, what will happen is we're going to have a, you can see that the red arrows are showing in the opposite side of the node, and that's indicating a compressive force. So basically, we're compressing that bar, and that can give rise to these compression forces. So when you move the bars around, you would realize that, okay, we actually get what we want, right? These red arrows are always along the axial direction of the bar, and it's capable of representing the compression and tensile force accurately. So we probably have done a very good job in creating these previous functions that we just finished. All right, so hope that gives you a good introduction of how we do the internal forces. And the next thing we hope to do is to moving forward and start talking about Hessian matrix and stiffness. So basically, we're moving on to start working on the second derivatives, right? So remember the first derivatives, Jacobian is 6/1. And because this potential function has 6 variables in it, if we take the second derivatives, we're going to be talking about a Hessian matrix that is 6/6. It looks annoying. Um, yeah, it definitely looks annoying. So if you want to solve the solution analytically, it's gonna take some time, but it's not crazy. It's doable. There's a lot of people have done it, and you can find this solution from many mechanics textbook and also in the vectorized code of this package. I myself had to do it analytically so that I can have the code vectorized for faster computation. But let's not worry about those things at this point. And let me show you how can we use a little bit of math and just to dramatically simplify how we can code to get the stiffness matrix right. All right. So let's take out the first column here from the Hessian. And this column has this structure here. And the cool things about this column, all these variables inside, is that they've all done a derivatives about xi. So using the the characteristics of multivariable calculus, we can actually take out that partial derivatives about xi. And the remaining part is something like that. It's the u bar taking the derivatives about xi, yi, zi, xj, yj, zj. This thing looks familiar, right? This thing is calculated. We just calculated. This is the force. This is the nebula x, nebula u bar about x. So nebula is inverse triangle. The name of these mathematical notation is nebula, just in case you don't know it. So we just calculated it, right? So we calculated as using this function, oops, excuse me, using this function here, and we just evaluated it using that example, and we believe that we've done a very good job in getting this function right? So if it's showing up here, maybe I can do something to reuse it, right? So let's see what we can do, right? So we look at the second column, third column, the fourth column, and we do a little bit of reorganization just like these, right? So for the first column, there's a common derivatives about xi. For the second column, there's going to be a common derivatives about yi. Third one is zi. Fourth one is xj, yj, and zj. But the thing is, all of the things inside here they're all nabla U bar about X. So that seems to be indicating something. So for instance, for this first term, what we need to do to get this using the central difference is basically just changing the U bar to nabla U bar about X. Right, so that's all we're doing here. If we use central difference to approximate this term here, right? So just stare at this function here, right? This is nabla u bar of x about xi. Take the partial derivatives about xi, and the only difference between these and let's say this function here is that we're changing this u bar to be the nabla u bar about x, right? So that's the only difference. So this suggests that in order to get a calculation right, all we need to do is just change the u bar to the nabla x. So this is new equation, and let's see how we can do that in the code, right? In the code, surprisingly, what you will realize is that the functions we've calculated the stiffness, the Hessian matrix for stiffness is exactly the same as the previous function, the one we used to calculate the force. So the only difference is that right now we're outputting a 6x6 Hessian matrix. The structure looks exactly the same. This is for node xi. This is for node xj. And there's going to be a forward step, identical. There's going to be a backward step. That's also the same as the previous function we just created, right? So the only thing we're changing here is change that potential function to be the local bar force, which is the nabla u bar about x. That's all we're doing, you know? If you do this using coding, it's just gonna make your life so much easier, right? And all of a sudden, you change these very intimidating equations to be copy pasting the code and then do a bunch of adjustment to it, right? So the only thing that we need to pay attention here is that just keep in mind the local bar force will feed out a 6x1 vector. And that's why this is going to be Ki. We need to feed basically this row here. So for the second term, if I is 1, this one will be here. And then the second one, it's going to be about xj. So when I is 1, it's going to be xj without a vector, the scalar xj. So that would be the fourth column. So this is node I, this is node j, x, y, z, x, y, z. That's the structure of the code. So really the only thing is that in the MATLAB, just remember the MATLAB notation about, when you fill the entire column, it's going to be a comma and then this thing here to fill the entire column. That's the only thing we need to pay attention to. So now that we have the function coded, let's try to test out how things work. Right, the first example is we're gonna put the bar along the x direction. We try to elongate it or make it shorter and try to see what kind of stiffness we're getting. Right, so let's run the code and try to see what we can get. This is we'll change the bars, the second node's rotate location. So basically we're changing it. And as you can see, so this line is where the stiffness is outputted. Nothing is changing in the stiffness. Does that make sense? It actually should make sense, right? So because we're dealing with a spring or a bar with a constant stiffness, that's why we're using, this 1/2 k delta squared. Basically, it's a constant stiffness, so it's not changing about your deformation. And also in our code, we do have specified that the bar stiffness, the K, at the very, very beginning, the K bar is 1, so 1 Newton per meter. So therefore, these things make sense, right? If we're measuring the stiffness along the x direction, this should be a constant 1, no matter how we deform it. All right, so the next thing we want to do is to verify it with another example. for this one. So what we're trying to do is we're going to measuring the stiffness of this bar along the x1 or the x direction. And as the bar is rotating from aligning to the x1 direction all the way to x3 is z, the z direction, and try to see how the stiffness along, the x direction changes. So let me actually draw this out. So that's the vertical, that's the horizontal, and these are the configuration in between. And we're talking about Z or X3, depending on which one you're most familiar with. So X is also X1, right? That's some of the common notations we might be using in mechanics. All right, and we track the stiffness about X1. So this is the result. We can see that the force, the stiffness is first 1 when the bar is along the x1 direction. Expected, it should happen, right? This is just like what we have here. But when the bar is rotated to the vertical location, the stiffness about, so 90 degrees, the stiffness about the x direction is 0. Does that make sense? It should make sense, right? In order for this bar to generate stiffness in that direction, it needs to be able to it needs to have some slanted it needs to have form an angle towards that x direction, right? If the bar is vertical, we know that from our basic mechanics that this bar is unable to provide any forces along the x direction just because the force from the bar has to be aligned with the bar. That's all we know about. That's the most important thing we need to know about the trusses, right? So if you have a bar that's has an angle, then whoops, the stiffness is going to be 1 in that direction, but then the portion that you get out of it is going to be smaller. So when you deform it, let's say by infinitesimal 1, 1 deformation there, then this is the case. So these stiffness should also follow a cosine function, which is exactly what we get here. And that kind of verifies the derivation of the element. So we would be quite happy with this result because it's not violating some of the basic physics and mechanics we've been learning since, I don't know, high school. So that's a good thing. All right, with that, let me keep moving down. And what we hope to do at the end is to just compare these functions we just derived with the stalk function, so stalk element functions. So we create a bar, CD bar element, and the way we can compute the forces out of the stalk function. So this is the result from the stalk function is self-local force. That's the function we can call from the bar element. And this is the nodal deformed nodal coordinates. That's the Young's modulus and area with a length of 1. With the L naught of 1, these two will give us an A that's EA divided by L 0, and that's also 1. So that matches what we have in the functions that we derive in this code. So let's take a look at what will happen, right? As you can see, when we are changing these nodal coordinates of the jth node, we always have the forces computed with the functions in this file, match that from the stalk element. So you can see that this vector is the same as this one, despite that they're computed using different functions. So this is using the stalk element, this is using the functions derived in this file. They always match each other, right? Of course they should, right? When you do mechanics right, they should give you the right result. So if they don't match, something's wrong. So mechanics never wrong. It must be the code that's wrong. So the same thing also happens with the stiffness. If we compare what we have from the stalk element with what we derive in this file, they matches each other very well, regardless of like the notation, the location of the second node, right? So they are always the same. You can just look at these two matrices and verify that for yourself. All right, so this is good verification, and we now have a, a relatively good idea of how we derive this bar element using central difference. So it's actually one thing I hope to point out here is that these method automatically supports large deformation, right? We're not limiting ourselves to small deformation. So for this particular example, we're doing finite rotation of these bars. These bars are rotating very large angles, but it still gives us the right result. So that's actually a nice thing about doing the central difference based on the potential of a bar because you don't need to be worried about extending, let's say, a linear element to a nonlinear large deformation element. So the one class that's most related to the material presented here would be finite element. So if you've taken that class, the typical finite element approach only allows you to capture small deformation. So we do the shape function, take the derivatives of it, and assemble the stiffness using quadratures to do the numerical integration, so on and so forth. But that approach don't automatically support large deformation. Um, in order for you to derive an element that can, that can support computing finite rotation without giving out, fictitious stress and strain, you need to do some extra work. And throughout one semester of grad level finite element class, you typically don't get to the point where you will learn those. So trust me, that's true in the current curriculum. So that's actually the beauty of the theories and the central difference method I'm presenting here. So you automatically support large deformation. That's very, very nice, really. But anyway, if you're curious about how typical elements are derived, I still highly recommend you to take the finite element class. It's definitely a very good theoretical class that will equip you with a lot of math tools and theoretical background. And the other classes that are relevant to the material presented here is like numerical methods. So central difference is typically delivered in classes like numerical method in math department, for instance. And you also could, it's pretty much a must cover methods if you, let's say, if you teach a class about a numerical method in civil engineering or a numerical method in mechanical engineering, or let's say an undergraduate numerical method class from the math department. This is pretty much a method you will have to cover. I don't think you would skip it. And the other place you tend to see it is in structural dynamics. So the civil engineering version of structural dynamics, you typically have a central difference method as part of a numerical solution methods for a initial value problem in a dynamic setup. And that's also where you can find these things. So hopefully this gives you an idea of where to look for the related materials. And the final thing is that, as you may know, in this source code, we have elements, bar element derived using C central difference, so CD element. We also have the vectorized version of that, so vectorized element bars. So those are based on analytical solutions. And if you do the analytical solutions, and it usually typically allows you to vectorize the code and allows them to solve and run faster. So if you want to learn how to do those things, the best references, I believe, is actually listed here is by a paper by Dr. K. Liu and also Glaucia-Paulino. Dr. Glaucia-Paulino, they have a wonderful paper here for the simulation of origami systems. So the link is below. That's the paper if you want to check it out. That covers a lot of a very detailed thing about deriving this bar element with hyperelastic bar element with the analytical approaches. So that's where you can also find the related materials to learn more about what's been covered. So, all right, so that's all I have for the section 05. And the next time, what we hope to do is to cover a little bit more material about central difference. So in this section 5, we're just dealing with one bar. Right. So what if we have multiple bars, and what if the assembly also has some sort of a support condition that we need to consider? So that's what we will cover next time. And following that, it would be the Newton-Raphson method for the nonlinear solver. So hope that gives you some idea what we're going to be doing next time. So with that, thank you very much for your attention, and I look forward to seeing you again in our next section. Have a great rest of your day.